The malloc function is the function required when you need to request memory from the operating system. You call malloc and you say to the operating system, I would like a certain number of bytes, please. The operating system will, if it can, give you those bytes, or at least it will set aside those bytes as being reserved for use by you and give you the address of the memory area that is set aside for that. Malloc is short for memory allocate, and it's one of the standard C library functions. This is how it looks. First of all, you must hash include stdlib.h. That contains the prototype for malloc. It also contains the prototype for several other dynamic memory functions. Anyway, somewhere in your main or somewhere you must then declare a pointer to something. A pointer to what? Well, it could be a pointer to anything. It depends on how you're going to view the memory when you receive it. You might say, well, I'd like to now dynamically create a floating point number. In other words, you're going to use the memory that you get. Hopefully you'll get enough memory to use as a floating point number. So you'll need, if it was a double, I guess you'd need 8 bytes. So you've got to ask the operating system for 8 bytes, and then you're going to treat that memory as if it were a double. In other words, you're going to write double-like information into it. And if that's what you're going to do, then you might say to yourself, well, the pointer that I create to point to that memory, I'm going to call it a pointer to a double. If you wanted that memory that you created to be an integer or even several integers, and we'll get to that in a minute, how it can possibly be several integers, then you would say that the pointer that you create is a pointer to an integer. And then it's easy. Then you just say, well, in this example I've got on the screen in front of me, I'd like 100 bytes, please. And malloc will go and get those 100 bytes, and it will put them in a memory area for you and give you the address of that memory area, which you should then assign to the pointer variable that you've created. Note that the variable called pointer, the actual pointer variable itself, is a stack variable usually, or it could be even a static variable. Whereas the thing that it points to is now going to be, well, it's not going to be a variable per se, but it's going to be memory that's on the heap. Just keep that in mind. I know that you're dealing with heap memory here, but the actual pointer that points to it is not on the heap. The pointer that points to it is just a regular stack variable usually. Okay, what else can we know about malloc? The size of operator is often used to specify how much memory is required. I mean, you can, if you like, say, okay, well, I want a double, and therefore a double is 8 bytes, so I'll just ask for 8. Well, a double is 8 bytes, but what if it changed one day? Or what if you had a compiler or an operating system that treated a double differently? It's much safer just to say, I don't want 8 bytes, I want the size of a double. Something like this. This isn't the double example, of course, but instead of asking in the previous example for 100 bytes, you might say, well, those 100 bytes are actually going to represent 25 integers, and every integer is 4 bytes. That's what I want to use those 100 bytes for. So you can make that more obvious to anybody reading your code. It'll be exactly the same to the compiler, but to people reading your code, the code that I've got now in front of you says very clearly that you want 25 integers. Now this is extremely important, extremely important. If malloc cannot find a chunk of memory of the requested size, in other words, you ask for 100 bytes and it actually can't produce 100 bytes, in other words, the system is out of memory, well, that's usually the case. The system is out of memory if it can't get that memory for you, although it could just mean that the entire malloc subsystem is all screwed up. That can happen quite often. Anyway, if all of that happens, malloc will return a value of null. Now, I can't stress highly enough, you have to check this. You have to put immediately after this malloc statement, you really have to put a statement that says if pointer equals null, then we didn't get the memory, and we have a serious problem because we're pretty much out of memory. We're certainly out of heap space anyway. Or if we're not out of heap space, then the whole malloc subsystem is screwed up, and I wouldn't like to rely on it for anything else in future, so you might want to find some way of quickly exiting the program at that point. You would be amazed at the number of people that do not bother checking to see if malloc returned the right value or not, to see if it returned something that wasn't null. They just think to themselves, well, there's going to be heaps of memory available, so using the word heaps in the large sense, so malloc will never return null to me. In other words, I'm always going to get the memory I ask for, just use it. And then one day malloc does return null, and they start using null as the address of the memory area that they were given. And as soon as they try and do that, the program just crashes straight away. So please put an if statement after your malloc to check that you actually got the right memory. I know that many of you are going to be working on systems with virtually unlimited memory, like many megabytes of memory. So you might think, well, I'm only asking for 100 bytes, so how could that possibly run out? Well, it may not actually run out. It may be that you've buggered up the malloc subsystem, and malloc may return a null when there is in fact heaps of memory available. You may still get a null value back, and that's something that you've caused. It's a bug in your system, and I can tell you how that might get caused. Well, I'll tell you that when we get to the free function, but it's usually got something to do with freeing up something that you never allocated in the first place, or even just repeatedly inside a loop, perhaps repeatedly mallocing and never freeing. And if you do that enough, you will actually run out of memory. Okay, what else can we know about malloc? Once the memory has been allocated, and this is really interesting, the pointer variable, which is it's a pointer, PTR variable in the previous example, can be treated exactly as if it were an array declared on the stack or declared statically. So what am I saying here? You can treat a pointer as if it were an array. You can treat a pointer as if it were an array. You really can. That might sound extremely odd to you, to treat pointers as if they were arrays. But I suggest that you get used to that idea very quickly. Arrays and pointers are almost interchangeable. Now I know that goes against the grain of all your understanding of C, but I will explain that in the next chapter, or I think it's the chapter on advanced pointers. Arrays and pointers are almost exactly the same thing. You might think, how can that be? I mean, a pointer is just a memory address. It's the address of something. And an array is a great big block of many things all run together. How can they be treated as the same thing? Well, again, I can only say that I'm going to show that to you later, but take that for granted just for the moment, that pointers and arrays are very similar. The only difference is when you try and evaluate their size. I mean, the size of a pointer is going to be almost always 4 bytes, because that's the size of a memory address. Memory addresses are 4 bytes. And the size of arrays, well, the size of an array is the size of the array. It's the number of elements times the size of each element. That's the size of the entire array. But now, I want to stress to you that that is the only difference between pointers and arrays. That and the fact that you don't actually have to initialize an array, but you do have to initialize a pointer. You must set the pointer to point to something. Anyway, I'm mentioning all that now in the dynamic memory section because I want you to be careful. Some of you might be tempted to use size of pointer. Let's say you allocate 100 bytes using malloc, and you set pointer to point to that. The temptation might be to think that the size of pointer, the size of operator, is now going to return 100 because pointer is pointing to something that is 100 bytes. That is not the case. The size of pointer, or size of PTR in this case, will always be 4 bytes, no matter how big the thing it's pointing to is. You really have to know that. In fact, I'll go so far as to say there is absolutely no way of telling how big the memory is once you have allocated it. There's no function that you can call that says, how big is this piece of memory that pointer is pointing to? A function like that does simply not exist. You have to keep track of it yourself. That's quite important. Anyway, let's now go and look at some examples using malloc.